Or the second ball is blue. In that case, the third ball can be green, red, or blue. So you have 5 choices. This will also be 5. This will be the sum of the other, the 3 numbers here. This will be 7. This will be the sum of these 2 will be 12. This will also be 12. And this will be sum of these will be 17. So this will be the sum of 12 plus 17. This will be 29. This will be 29. This will be added together. So 12 plus 12 will be 24. 24 plus 17 will be 41. So that's this table. The next question asks you how many options are there selecting 5 balls. So that will be the sum of these 3 because the first ball can be either one of the 3 colors. So this one will be 29 plus 29 plus 41 will be 29 plus 70 will be 99. So that is the answer. Any questions? Does this make sense to you? You got it right?
Actually, I would have got it right, then I accidentally added 4 more. So I had it right originally, then I changed it.
You wrote it right, and you should change it to wrong.
Yep.
Sorry about that. Okay. Any questions about this? Okay. The next question asks you to understand what happens if you have a recursive function and it is incorrect. As I said before, I'm looking for your understanding, I'm not looking for your memorization. So I told you, this is incorrect. This is a mistake. It should be middle plus 1, but it's right middle here. And if this were correct, and it's also said it here, if this program were correct, the output will be 0, 1, 2, 3, 4, 5. Why? Because you are simply searching the values in the array. Right? You try to find an index, and you are looking for the element in the array. If this search is correct, you'll simply return the correct index. Since it goes through the array elements one by one, it should go through 0, 1, 2, 3, 4, 5. However, because of this mistake, it says because of this mistake, the recursive call will not end for some cases. For each of these cases, the program eventually runs out of memory for the call stack. Basically, that means your recursion does not end. To put it another way, somehow the numbers do not change. So you just keep calling itself and again and again. So please write down smallest value of int in main when the program runs out of memory for the call stack. And write down the value for key, low, and high at the top of frame when it runs out of call stack memory. This is actually a simplification of a question from last semester. And if you remember, I actually told you to study that question. Let me first put this. This is the answer. The index is, oh, you don't see that? The index is 1, means that when you have the second one, it will not end. When index is 1, the key is 12. That's 12 here. And the low and the high will be 0 and 1. So they will just never end. And this is the call stack. When you have 1, I assume the array address is at 10,000. Then you come here, your low and the high will be 0 and 10. And mid will be 5. You come down here, you take the previous one says mid minus 1 here. So your high becomes 5 minus 1 becomes 4. And your low doesn't change, so it is still low because it's less than, it's at the beginning of the array. So come down here, you take a mid minus 1, mid minus 1. So 2 minus 1, and you get 1 here. And mid is 1 divided by 2, it becomes 0. So low is still 0, key doesn't change. We don't change key inside the search. Then you come here, so low is 0, high is 1. Mid is 0 because 1 divided by 2 is 0. Then here you do mid, instead mid plus 1. Therefore, your low stay with 0. Your high doesn't change. So you look at these two frames are the same. Therefore, you can't get into a recursion that will never end. Try to convince you that I have given you a hint. Some people actually talk to me after the exam. They say, oh, this question is very similar to what we have seen before. That is correct. So if you look at this question, for last semester, that was a different mistake. Mistake on line 3. It should be larger than, not equal. Does not include equal. What happens if it includes equal? Why is that a mistake? This is from last semester. What happens if it includes equal sign? I thought some of you practice this something. On the class? What happens if it includes equal sign? It should be larger than, it doesn't have equal sign there. That's, if it's correct, it should not have equal sign. Now with equal sign, what happens? Why is it a mistake? When will you return minus 1? Give me a scenario when you return minus 1. When you have low equal to high. And why would that be a problem if you have equal sign? When low equal to 1, what does that mean? You still have a 1 array element to search. You say one more, the last one. Right? You start with a big array, you reduce by half each time. Right? So you have a lot of elements, you reduce by half each time, and at the end you have one less element you want to check. If you still cannot find, this key doesn't exist in the array. If you have an equal sign, you don't check the last one. But there's one more element to check, one last element to check. In that case, you return minus 1 even when that element is actually in the array. So the question for this semester is a bit simplification in the sense that last semester we asked you to fill in all scenarios. This semester only asked you to find the smallest one. Any questions about this? Why is the problem? Any questions about this? Why is this going to run out of stack memory? Do you know what? Do you understand?
For last year's problem, or
For this year's problem.
this year's problem? Yes, because it continuously calls itself without changing any of the values.
Right, because this is mid is integer division, so 1 divided by 2 becomes 0.
You might want to change.
Oh. 1 divided by 2 becomes 0, therefore you never change. So that's the same. Okay, any questions? Okay. The next question seems pretty long, but if you understand this kind of question, you will look for specific things in the program. So this is a structure with integer and data. This is a pointer because there's a asterisk there. We specify the length is equal to 10, and we specify file name as data. Then we create a pointer. We first ask you, what's the size of this? What's the size of this? It's a pointer, right? This is a pointer. So we give you information here saying assume this program runs on 64-bit machine processor and one integer uses 4 bytes. That's where we give you the information. If it's a 64-bit processor, means it needs 64-bit space to store address. That means a pointer has 8 bytes. Assume the program never return exit failure. Okay, so what's the size of this? Since it's a pointer, its size is going to be 8. This is a derivation of the assignment. I think the assignment 5, image processing. Right, image processing. We told you the header is, how big is the header? Do you remember? Did you do an image processing assignment? No. Who did an image processing assignment? Nobody did an image processing assignment? Really? Did you do the image processing assignment? Wasn't there an assignment for image processing?
The one for this class?
Excuse me?
The one for this class?
Yes.
Yeah.
Is that assignment 5?
Yeah.
Do you do that?
The
Yeah.
BMP.
Do you do that?
I don't remember.
Yeah.
Do you do that? Image processing? Yeah. Okay. So why did not anybody say anything? Do you do it?
Yeah, I remember the second file. I mean,
Okay. So the header file is 54-bit, 54 bytes. Do you know how to get 54 bytes? Have you ever asked that question? How do you get 54 bytes? That's you add them together. You add the length of them together. That's how you get 54 bytes. And here we also say pack 1. If you go back to your image processing assignment, that's on the top of the assignment. What this means is, for performance reasons, compilers sometimes may move data around. So if you say, I need something for only 1 byte, compiler may say, I give you 4, because it can be faster. When you take 362, you will understand why it can be faster that way. It's called alignment problem. If you don't say pack 1, you give compilers the freedom to align. When you say pack 1, you tell compiler do not align. Means if an attribute needs only 1 byte, give me only 1 byte. Don't give me 4. Don't give me 8. I want to pack them as tight as possible. 1 means use byte as the minimum unit. So this means do not add more space. As I just said, if without this line, you give compilers the freedom to add more space so that your program may be faster. Right. That line is in assignment 5. If you don't believe me, I can show you. I'm pretty sure it's there. Right? It's right here. tell GC not to pad structure with actual bytes, sometimes including for performance reasons. Okay, but that's not how we are testing. We simply tell you that we do not allow compiler to add additional space. Okay, so this will be 8 because it's a pointer. Pointer needs space for 8 bytes since it's a 64-bit machine. Then we allocate the memory. Then we ask you again how much space this needs. It's still 8, right? So what this means is in your stack, you have ARR, PTR. After malloc, you simply change this. You are not changing the size of this. This needs 8 bytes because this one needs to store an address. Since it's a pointer, that means the value is an address. Address 64 bits, therefore you need 8 bytes here to store the address. That's the reason this is still 8. We ask you what's the size of a type, the data type. The size of a data type is the size of the sum of these two. So the size of array will be the size of integer plus the size of integer star. That's the two attributes here. Size of integer is 4. Size of a pointer is 8. Therefore, this will be 12. So we ask you here, this will be 12. Then we ask you again, we allocate space again. What is happening is this allocate space, that's a 10,000. In your heap memory, you have length, you have data. So this address will be 10,000. We allocate additional space, that means this one will be another address, that's a 20,000. So I have 20,000. That points here. And I still need 8 bytes for this pointer, right? I'm changing the value, I'm not changing the size. Therefore, this is still 8. What's the size of data? Data is a pointer, therefore it is 8. So as you can see, we are using the same concept again and again. Simply saying, when you allocate memory, you are not changing the size of the pointer. The only thing you are doing when you do malloc is you are changing the value. You are not changing the size. Does this make any sense? Any questions? Does it make sense to you? Okay.
You said malloc change what?
Malloc changes the value. Malloc doesn't change the size. Okay, so the next will assign value to data will be 0, 1, 2, 3 until 9 because the length is 10. Then we open the file for write. We write so many bytes into the file. And the question says this program never return exit failure. So don't worry about error handling. I also say for simplicity, this program does not handle errors. Otherwise, this program will be pretty long. Every time you do malloc, you check. So this program will be needs another page. We just make it simpler. Okay. Then after this, you ask where is the file pointer. So you have written the size of this. This will be 12 because that's the integer, the size of integer plus the size of pointer 12. So the answer here should be 12. However, some people ask me a question: is it before or after or right after at 12? So the answer is 12, but we'll accept 11 or 13. If you write 11, that's fine. If you write 13, that's fine because you can say it's At the beginning or at the end, do you start with 1, do you start with 0? So we say, okay, as long as you understand it's somehow around 12, that's fine. But you cannot write 40. Because this only writes the size of 12. It does not write data. That's the problem. If you understand assignment 5, the image processing, why do we read header before we read data? Because you cannot write the pointer variable. This one will write both the length and the variable pointer. Does that make sense? If you understand assignment 5, you need to understand why you need to read the header before you read the data. Because the data is going to store in the memory. It doesn't make sense to write memory address into file because every time you allocate memory, you get different address. So then we want to release the memory, but before we release memory, we fill in garbage. Just make sure it's garbage. So we said fill the array with random variable, ensure the heap contains garbage variable before releasing it. That means this will be garbage. And that's another hint for the exam, you need to understand why we say it's garbage, because later on when we try to read variable from that memory location, it will be garbage. So we release the data, release memory. When we write this, the length is 10, and the data is 20,000. Why? Because I assume I call malloc and get 20,000. But that is meaningless. Because you write the memory address to a file, next time you do not have, it's very unlikely you have that piece of memory again. It comes from malloc. So then we allocate another object. We try to read the file. So at this point, after you do fread, array ptr to length. What is length? After you do fread. Want to try? Suppose there's no f open arrow, there's no f read arrow. What would be left? Okay, let me go back earlier and ask you, when you do f write, what are you writing? On line 30, what are you writing? That will be 10. You write 10, the variable 10 to the file. Right? What are you writing data? What will be the file store? You write whole object, right? Object contains length and data. What's data? What's the type of data? It's a pointer. And I said assume malloc give me 20,000. So you write, what do you write to the file? Which will be whatever malloc gives you, right? If malloc gives you 20,000, you are going to write 20,000 there. Okay? So you write 10 and 20,000 into your file. When you do fread, what do you read? What do you read?
Same thing.
Which will be?
10 and 20.
You'll read 10 and 20,000 from the file. If you look at line 30 and line 53, they are symmetric. So you should write something into the file, you should read the same thing back from the file. Does that make sense? Does this make sense? Okay, so this one will be 10, this one will be 20,000. Okay, we already said assume the program never exit failure. So what is the problem? The next page says there will be a problem, right? We already finished this part. We'll need to worry about sum. We'll deal with that later. It says 0 point tells you there's one or more memory error. What is the problem? What is the problem? Yes?
Trying to access the memory location 20,000, but it can't anymore because it's already free.
So on line 62, you try to access memory starting from 20,000. How to get 20,000? Because your F read, line 53, read 20,000 says, I'm going to access memory location 20,000. But that 20,000 has already been released on line 47, right? So this means free memory at address 20,000. You no longer own that piece of memory here. This has been released. And you try to read. So that's the problem. Sum will simply be garbage. Now I intentionally wrote random numbers here so that this will be filled by garbage. Because it's possible that this piece of memory has not been allocated to somebody else. In that case, you try to read that piece of memory, your program may not crash. Your program should crash, but your program may not crash. If your program doesn't crash, you will try to read the value here. Then in that case, that's still garbage, since I already cleaned up by giving random numbers. So sum will be garbage, and the problem is line. The next question is, ask you which line will be the problem and what's the reason. So problem will be line 62, and the reason is did not allocate memory for data. That's the answer for the second question. But we also accept, actually I intended to have F close here, but since I forgot. So we also accept, you'll say there's a memory leak because no F close. That's fine. That's perfectly fine. That's another mistake. But what is not accepted is memory leak because that is not accepted. Can anybody tell me why? Some people wrote that this program will have a memory leak because we did not free ARR PTR2 data. And I said that's not accepted. Why? You understand what I mean? What do you write? How about you? You know why I said that's not accepted? Because I never allocated memory for AR PDR2 data. So there's no memory leak because of AR PDR2 data. Does that make sense to you? Okay, any questions about this? Yes, please.
Does the file pointer take on a special value when it reaches the end of file character?
After you reach the end of the file and you try to read again, you will return a special character called EOF, capital letter EOF.
Okay, but that's after you read past the end?
After you pass the end, yes. Yes?
Is the size of all, any pointer 8?
No. So,
on this kind of machine.
so That's the reason I have to tell you which machine we are using.
Yeah, so on this machine, every pointer would be 8, right?
Yes. Actually, that's a simplification. There are machines where they have 2 different sizes. In some machines, their pointer, I'm not sure where I want to get into that detail. Newer machines are all 64 bit. Probably the machines you buy, I mean the desktop, the laptop, probably not your phone, not yet. Okay, all 8 bytes for the pointers. In the 90s, when machines were 32 bits, but people say I need more space. So in the 1990s, you have machines with somehow kind of strange addressing space. So their instruction is 4 bytes, but their address may be 6 bytes. When you take a course on computer architecture, 437, you probably will learn that. But here I don't want to get into that complicated situation. So here just say it's 8 bytes. Okay. Does that answer your question? I don't really answer the question. I just say let's simplify it and assume it's 8 bytes. Okay. When you take computer architecture, you'll learn that. Okay. Any more questions? Okay, the next question asks you how to deal with swap. It's a variation of a swap function we have seen many times, and as I have suggested to you, you should understand swap very well, because that's a very good example for testing understanding of stack and pointer and so on. So first, let's understand what is T and U. T is an object. T doesn't have a start in front. Therefore, we'll have in the call stack, T, since this object structure has 2 pointers, so we have T dot X, T dot Y. We have that simply because there is no star in front of T. However, X and Y both are pointers. Thus, we need to allocate memory. That's why we are doing here in line 61, 62. We also have U. So U dot X, U dot Y. Then we allocate memory. Suppose this is 10,000, 20,000. So they refer to heap. This will be 10,000, 20,000. This will be address. This will be value. So after line CD4, that's what we have in our memory. And line CD5 says take X, T dot X equal to assigned to 2. So T dot X value is 10,000. I put the star in front of the address. That means I want to modify the address, the value at address here. So this will be 2, 6, minus 4, and minus 3. Do you understand what's going on?
Yeah.
Yes? Okay. The next step is I'm going to print T and U. So print T, print T1. Actually, I think I didn't use T2. Originally, I intended to write another problem, but I did not. So we simply print the label T, and this will print it as 2, 6, minus 4, minus 3. So 2, 6, minus 4, minus 3. So that's line 69 and 70. 71 calls the swap function with T and U. T and U are not pointers. And this swap function also is not taking pointer. The swap function take object A and B. Therefore, You have A. Since it's an object, so it has attribute A dot Y, B dot X, B dot Y. You copy the attribute one by one. So this will be 10,000. This will be 20,000, 30,000, 40,000. It's copies. We said before, if you have an object 1, if you write something like this, that means you copy attribute by attribute. So that's the reason you have 10,000, 20,000, and so on. So now we are in this function. We have temp. Temp is a local variable. And it's not a pointer, therefore we have x and y as well. So when I say temp equal to A, and A is 10,000, 20,000, so when I say temp, let me use another piece of paper. When I say temp equal to A, as I just said, it's going to copy attribute by attribute. That means temp dot y is 20,000. Temp dot x is going to be 10,000. That's what happens here. Then they say A equal to B. So that means you copy B's attribute to A's attribute. So A's y, A's x, A's y will become B's y. So B's y is 40,000, so it becomes 40,000. This will be 30,000. And then the next line says B equal to 10. So B's x, B's y, B's x, this will be 20,000. This will be 10,000. So that's what you're doing inside the swap function. When the swap function ends, everything in the call stack for that frame gets stored away. Therefore, when you print, nothing gets changed. This will be exactly the same thing because you simply store away what's in the call stack. Okay? Any questions? The next one, okay, so I assign again so that you don't, if you make a mistake in swap 1, you won't make a mistake in swap 2, right? We prevent error propagation. What I want to say is, if I don't have, this one will reset. So that whatever you wrote here does not affect what you write here. That's how we otherwise if you make a mistake here, even though your thinking is correct here, but since you made a mistake earlier, everything will be wrong. So the purpose here is to reset so that you don't get affected by earlier mistake. The next situation is we print T and U again, so it will be 2, 4, minus 4, 2, 6, minus 4, minus 3. And the next we ask you to do swap 2. Swap 2 use pointers. So in this case, let me use another piece of paper. I'll draw it here. So you have T dot x, T dot y. So this will be, let's say this is a 100, and 100, since I said pointer is 8 byte in the previous question, so I just assume it's 8 byte again. $116, $124. Now the address of T is going to be the address of the first attribute. So the address of T is 100. Address of U is 116. It's the address of the first attribute. So I pass address T and U to swap2. Let's see what's doing in swap2. So swap2 has a pointer A, pointer B, and it has a local variable T and P. A is the address of a T, therefore its value is 100. B is the address of U, B's address is 116. Temp is the value of A. Temp is not a pointer, so temp has X and Y. Temp is not a pointer. There's no star in front of temp. I say temp equal to A star A. Now, I'm not declaring A as a pointer anymore because there's no type. The difference between this one, there's a type in front of star. This one, there's no type in front of star. If there's no type in front of star, means I will take S value as an address, read the value as that address. So I'm going to copy 10,000. I take 100, go to the value at that, read the value at 100. So that's 10,000, and it's 20,000. Does everybody see that? Are you with me? Temp is not a pointer. Therefore, temp has X and Y. I say star A means I take S value as an address, read the value as that address. So I take S value is 100. How to get 100? Because I pass the address of T into a function. Address of T, assume is 100. Therefore, A's value is 100. This means I will take A's value and go to read the value at that address. So I go to address 100 and read X and Y. So I get 10,000, 20,000. So that's what this line does. The next says star A equals to star B. A is a pointer. So I go to address 100. It's on the right side, star B means I'm going to read the value from here. Because B's value is 116. Star B, I'm going to read the value here. I assign to star A is here, therefore this becomes 30,000, and this becomes 40,000. That's what star A equals star B does. The next line says star B equals 10. So star B is 116, so come here. This becomes 10,000. This becomes 20,000. So I have switched the value in the pointer. I have not changed the value at that address. I changed the value of the pointers. I have not changed the value there. Therefore, when you print T and U, if you want to print T, it's going to print the value as 30,000 and 40,000. If you want to print U, that will be the value of 10,000 and 20,000. So when you print at line 83 and 84, the values have swapped. Therefore, this one will be -4, -3, 2, and 6. Are you okay? You're nodding your head. Okay. So now the next question is swap 3. So I initialize it again. Now be careful that the addresses have changed, but that's okay. Now the addresses have changed. Based on this, the address now is u.y So now this is 30,000, 40,000. That's in the stack. And it's a heap. Before I move forward, I reset it again. Therefore, this is 10,000, 20,000. $30,000 now is 2, 6, minus 4, minus 3. I reset it so that if you made a mistake earlier, that mistake will not come here. Now print again. It should not be a surprise to you. We should get 2, 6, minus 4, minus 3 again, right? 2, 6, minus 4, minus 3. So now I call swap 3. Swap 3. Swap 3 is not a pointer. So I have A dot X, A dot Y, B dot X, B dot Y. Right? It's not a pointer. I also have temp. Temp is a pointer. So temp is going to store the value of AX. If I copy, this will be 30,000. This will be 40,000. Temp is a pointer, and I will take A dot X. A dot X is 30,000, so temp will become 30,000. That's what line 38 does. Then I say SX equal to BX. SX 30,000, so I assign BX. Therefore, this becomes 10,000. That's line 39. BX equal to 10. BX equal to 10, so this becomes 30,000. That's line 40. 10 equal to A dot Y, this becomes 40,000. SY equal to BY, BY 20,000, so this becomes 20,000. And BY equal to 10, so this becomes 40,000. That's what happens in the swap function. When the function ends, everything here gets popped. When you print, you still print 2, 6, minus 4, minus 3. So it's not changed. 2, 6, minus 4, minus 3. The last question asks you to call swap 4. So this is the stack and the heap, what it looks like now, and we need to get rid of the top since swap 4 use pointers. So swap 4 requires A and B, they are pointers. Therefore, A is the address of the first attribute is 100. B is 116. That's in the code stack. And swap 4 says temp equal to AX temp. So AX, A is going to take 100. X refers to this one without a star. This one means 30,000. If I print, if I ask what is AX. You take S value is 100. You go to 100. X is the first attribute, so you read the value from the first attribute. Therefore, it is 30,000. And then you add the starting from. So you say, I want to go to 30,000. Did I make a mistake? X 30,000. I think I made a mistake here. It should be 2, 6, minus 4, minus 3. Because I reset it again here. So you take 30,000. Therefore, 10 is going to go to 30,000 read value. This will be 2. Then the next one says SX is BX dereference. So SX, you want to modify this. Actually, no, you want to modify this. You cannot see. You want to modify this. When we say SX, A is 100. You go to 100 and look at the value is 30,000. So this whole thing is 30,000. When we say, means this one you are going to modify the value at address 30,000. So you are going to change this value. Basically, you are going to change B's X into SX. So B is at, so 10 should be 30,000, so this should be 2. And B is 116. So B is 116. B's X is going to be 100,000, 10,000. Star BX is the value at 10,000, and it is 4, minus 4. Therefore, what you're doing is you are going to take this one is minus 4, assign to that location, this one becomes minus 4. Oh, you cannot see. And then you say B's X change to 10. 10 is 2. So B is 116. 116 come here 10,000. So this becomes 2. This becomes 2. So after this, you change the value to be 2, 6, minus 4, minus 3. And when you print, you'll print in the reverse order. Minus 4, minus 3, 2, and 6. So to summarize, this is when you have a pointer to an object, a structure. If you say AX, you take S value is 100, and X, you go to 100 and read the first attribute. If you say AY, you go to 100 and go to a second attribute. Now if it's a pointer again, you go to another address, follow that. Alright. Any questions? I know this needs to be careful. Yes, please.
Yeah, are there recursion and structure language that's going to be on the access?
Yes. So for this exam, we test 2 learning objectives. If you get the I think I took out that page. So if you get 5 points or more in the sum of the first 2 questions, so in this case, if you get 5, you add these 2 together, get 5 or more, you pass the first objective. You add the sum of these 2 questions, and if you get 5 or more, you pass the second objective, and you will show up again in the next exam. Okay. As I already told you a few times, we have 4 exams. We only count 3. So that way, if you didn't do well in one particular exam, that's fine. Okay. Any more questions? Was the exam hard? Easy? Tricky? Trap? Tell me.
It's hard.
Okay, why is it hard? What can I do to make you feel the exam is reasonable? Which question was hard?
3.
Question 3.
Question 3. Why is that hard? Tell me more.
Just, I think personally, I don't really understand the size of the function, something like that. So
Okay.
that's my problem actually.
So you don't understand how size curve works.
No, I understand.
Okay, anyone else? Yes?
After question 2, I didn't really like how easy it was to go and get like no points for it at all. If you had the wrong index, then everything else you could possibly do was wrong.
Yeah.
I didn't understand you. Say that again.
Okay, for question 2, I'm just saying I wasn't, if you had the wrong index for part 1, it's impossible to get any else of the question right, so I thought it was maybe too easy to lose all the points for that.
I see. Yeah, so you have to, because those questions are together. Yeah. Right. It's not possible to answer 1 without understanding 2. It's not possible to answer 2 without understanding 1. So I always encourage, if I have not said that, I always say this if I remember. Share your questions. If you don't like the questions, write your own. When you write the questions, you really understand the material. And actually, in the past, sometimes students did give me questions, and the questions are very, very hard. So end up, I didn't use students' questions, not because they are too easy, but because they are much, much harder. So I encourage you to write questions. Okay. And in some cases, if your questions do show up in the exam, I assume you'll do very well. Right? So I encourage everybody to write questions. Because really, when you write questions, you understand what is being asked. You go to the course material, go to the assignment, you say, what does this assignment ask me to do? What is expected from this assignment? Does that make sense? So why don't you try to write some questions? Don't make it too hard. Okay, anything else? Any other suggestions? Do you have enough time? Is time the main problem, or it's the difficulty of the problem? You have enough time. You want to say something?
I didn't think there was enough time for this one.
You didn't think enough
Yeah,
time?
I thought it
Yeah,
was way
this one
longer
has
than the
less
first.
time.
The first one was reasonable. This one was really long.
Okay. Is it because problems are difficult? It's not a lot of writing though.
No, it just takes, especially when there's like 4 pages of code.
Okay.
It takes a while to go through it all.
Okay.
Even if you know.
So make the code shorter.
Yeah, even if you know how to do it, it just takes a while to step through everything.
Okay, so maybe like question number 4, only ask 2 of them instead of 4.
Yeah.
Okay. Anything else? Is the exam hard or is too long, or both? Both? Okay. So, do you volunteer to write the next exam? Thank you.
Yeah.
Okay, great. Okay. Really, if you write exact questions, you do learn better. It's not easy to write exact questions. If the exam is too easy, we become pickier when we grade. Do you know what I mean? That's just the typical situation. Even though we don't do that intentionally, we just say, okay, this question is so easy, so you should not make small mistakes. So that's the typical situation. All right. For the next assignment, we'll ask you to start using binary tree to do what we call compression. There are different types of compression. The basic concept of compression is reduce unnecessary information. Let me use the other page. I don't like the line. So compression is to reduce unnecessary information. Let's imagine a situation, or that's not imagine, it's in real life. Let's say in an article, in an English article, which letter do you think will be used most often? Do English letters appear at the same frequency? A, B, C, D, F, G, H, I, X, Y, Z? Okay, so which one will usually appear more often? E. Anything else? S. Which one will appear less often?
Z. Z.
Z.
X.
X.
Q.
Okay, so let me give you an example. This is actually from the class note. So when I wrote this class note, I just randomly picked an article. It's a United Nations Charter. It's not character, I typed it wrong. It's a Charter of the United Nations in 1945. So I wrote a very simple program to count the occurrence of the letters. And this is in the table. So how do you read this table? The first column is the value of ASCII code. So 10 corresponds to new line. 32 corresponds to space. And there's other symbol A, B, C, D, and so on. Right? A corresponds to S65. So as you can see, in this particular article, A show up 21 times, and B show up nothing. Capital letter B. Capital letter C show up 15 times. Capital letter W, X, Y, Z didn't show up. Lowercase a show up 105 times. Lowercase b show up 38 times. So you can simply glance through, right? So for example, article, that's a capital letter A and capital letter A, and this is a lowercase a here. So this is an example where you have an article, some characters show up more often, some characters show up less often, and some characters do not show up at all. If you want to transmit this article, give this article to somebody else, one simple solution is to use the ASCII table. You say A corresponds to 65, capital letter A corresponds to 65, capital letter B corresponds to the number 66. That's one way to do it. But that's not efficient because you also allow some letters, they never show up. For example, lowercase k never show up. What you want to do is you want to be more efficient. You want to say if something does not show up, I don't have to have a way to say it. Does that make sense? You want to say if those letters show up, then I tell you the letters show up. If the letters do not show up, you simply do not tell the receiver. Moreover, if a letter shows up more often, for example, let's say you look at this E, lowercase e, show up 263 times. Compared to capital letter X, it never shows up. Or compared to another letter, let's say lowercase x. Lowercase x only shows up once. You want to use fewer bits. If you want to communicate this article to someone else, you want to use fewer bits for the lowercase e, because it shows up so many times. If you use fewer bits for lowercase e, your article becomes shorter. The principle is the following, and this is a fundamental principle in many engineering design. Is we call make common cases faster or efficient, more efficient. E appear often, you want to use few bits. X appear rarely, you can afford to use more bits because it doesn't show up often. And together you use overall few bits. So this compression, the first step in the compression is to count occurrence of each letter, as shown in this table. You first count occurrence and determine which one is more often, which one is less often. Then the next step is to determine how you are going to represent the frequent letters and the less frequent letters. We are running out of time, so I will stop here.